Matt Miller with you at Trekzone HQ. Well, it's just gone 10 to 3 in the morning and we're standing by to take you live to Coober Pedy, where we have exclusive access to a camera ready to capture the fireball of Hayabusa-2 as it hurtles through the atmosphere for a landing somewhere in Woomera.
Beaming around the world with the latest science and space news on Facebook Watch, YouTube, and wherever you get your podcasts. This is Talkin' Science with Dr. Brad Tucker and Matt Miller.
And this is that live shot of the skies above Coober Pedy, thanks to a webcam at the Umoona Opal Mine and Museum. We're going to be keeping a close eye on that as the morning progresses, as well as chatting with Glen Nagle, detailing how Tidbinbilla and the other dishes in the Deep Space Network communicate with spacecraft like these. Plus, geologist David Flannery will beam in for a chat with what this sample means for the community, as well as his work on the Perseverance rover on its way to Mars. And Osiris-REx project scientist Jason Dworkin spoke with me about the lessons Hayabusa has taught their team and what their mission hopes to achieve. But of course, it wouldn't be Talking Science without Dr. Brad Tucker giving us all the facts. And let's bring in Brad Tucker now, Talking Science co-host. Brad, thanks very much for your time this morning.
Yeah, an exciting early morning for a return from millions of kilometers away.
It is incredible to think that Hayabusa-2 has been to an asteroid and back with this decade-long mission.
It really is. You know, it's been something that's built years ago, took years to get there, spent, almost 2 years at least in orbit and doing its scientific awesomeness, and then had to make its return journey back. So it's been a long wait for everyone, and everyone's excited to see it land and get in and see what surprises it has locked away.
And it's been 18 months, very similar to Osiris-REx, and we're going to be talking about that with Jason Dworkin a little later on. But similar to Osiris-REx, it spent some time around Ryugu, gearing up, closing everything off, gearing up, ready for its return.
Yeah. So after it popped off the surface, it didn't just immediately scuttlebutt out of there. It did some further follow-up observations and data, just as it did when it arrived, doing its surveying, and then at the right time, both in terms of distance between Ryugu and Earth, and after the science was done on the asteroid or at the asteroid, got out of Dodge, so to speak, and made its return journey all the way back to Woomera, which we're seeing this morning.
Well, Brad, we'll be back later in the live stream to continue chatting about the Hayabusa-2 mission. For now, though, we are standing by to bring you the fireball as it roars across the South Australian outback skies. We have exclusive access to this Umoona Opal Mine camera trained on the northwest, and we'll bring it to you live right here on Talkin' Science on Trekzone. But that's not all. Tidbinbilla's Glen Nagle will drop by to tell us how the Deep Space Network keeps scientists and mission control in contact with Hayabusa-2 on its way through the solar system. Plus, we've got Professor David Flannery standing by to answer the burning questions about what we can learn from these samples. But if I press those buttons, you'll be able to see me again, and I can say that we're going to dive into my chat now with Jason Dworkin. With the other near-Earth asteroid mission that is currently underway, NASA has this mission. It's called Osiris-REx, and it tagged Bennu a few months ago, and the team on the ground are preparing to command the spacecraft to return home, where it will land in the Utah desert, somewhere in the Utah desert, in 2023. Jason, thanks so much for your time today, man. I really appreciate it.
Thanks for having me. It's a pleasure.
You're a project scientist on Osiris-REx. What exactly does that entail?
So Osiris-REx is a PI-led mission in the NASA's New Frontiers line. The PI, the principal investigator, is Professor Dante Loretta at University of Arizona. My job is to help him out. I'm the government person helping out to make sure that we maximize the science and also understand engineering realities. So my job is to help the science team know when they're destroying the engineering and breaking the budget, and help the engineers know when they're destroying the science.
That must be a very difficult balancing act.
You're always the dumbest person in the room because you're always with experts in another field. And so what that means is you have the opportunity to ask dumb questions and come up with sometimes interesting solutions.
It must be tough to balance those two sides of the mission as well. One, very, very different sides of the mission, but obviously aiming for the same goal.
Oh, it's a very interesting position to be straddling between science and engineering and management. It's actually very rewarding to be able to enable more science to be achieved than you can possibly do by yourself in a lifetime.
Now, the Osiris-REx mission, it's a very cool one. I think it's the third near-Earth asteroid sample mission after Hayabusa and Hayabusa-2. What's the sort of goal? Well, what is the goal with Osiris-REx?
So Osiris-REx goal, we started out with the mission concept in 2004, before we even had heard of Hayabusa-2. And to learn what we could from Hayabusa and Stardust and Near Shoemaker missions, to go to a primitive asteroid, carbon-rich remnants of the early solar system, and get a large sample to bring back to Earth to study in laboratories around the world to understand the origin of the solar system, the origin of planets, and perhaps the origin of life. And
Osiris-REx is an acronym. What does it stand for?
NASA loves its acronyms. Osiris-REx is the objectives of the mission, and developed by our PI, who's very proud of this acronym. Origins, spectral interpretation, resource identification, security, regolith explorer. And so each one is a mission component. So origins, origin of the solar system, origin of life, is from my perspective, the principal objective, because that's what I'm interested in. Next is spectral interpretation. There's almost a million asteroids in the solar system. We're not going to go visit every one of them. So by looking at this asteroid, comparing what we see in space versus what we see in telescopes on the ground in Earth's orbit, we can try and better understand and ground truth what we observe from the sample, from in situ, and from the ground, so we can better understand how to interpret our spectra of other objects. Resource identification. Someday, perhaps soon, there will be asteroid mining happening to further exploration of the solar system, be refueling depots or what have you. And so by exploring such a small body, learning how to navigate around a small object, and how to understand the resources that this near-Earth asteroid has, will help resource identification. As to security, so Bennu has a 1 in 2,700 chance of hitting the Earth a long time from now, in the sometime between 2175 and 2195. That's 22nd century, a long time. But understanding its orbital parameters will help us learn how to deflect asteroids. This one in particular, and asteroids in general, as we learn their properties, has been called the Arkovsky effect, which is a non-gravitational thrust that small spinning asteroids experience because of differential heating as they rotate. And so by understanding this, we can better predict asteroid movements in the far future. And then REx is Regolith Explorer. That was an acronym we added on at the end because Osiris-REx was our third try at getting this mission accepted. After 2 Osirises, who became Osiris-REx, bigger and better with a better instrument payload, able to analyze the regolith, the surface rocks and dust, down to the sub-centimeter level.
Wow. What's it like as a team to watch the rocket launch with its payload, the very precious spacecraft of Osiris-REx, to watch that launch and then trust that it's on its way? There really isn't a lot more that you can do while it's on the way, except wait and hope that it's going to make it and complete its objectives.
Well, there's a lot of work in between. So we spent years designing and testing the spacecraft so that we would know that it would behave properly. And it's actually been a marvelous spacecraft. It's been almost trouble-free. We've had a wonderful team that works very well together and has been able to overcome challenges as they come about. We've had quite a few. But when you launch the spacecraft, you check up on it all the time. We use the Deep Space Network to communicate with the spacecraft during its outbound cruise and make sure everything's fine, do course adjustments, fiddling, things of that sort. Now, that means you can't make changes, and that's the value of sample return, is when you have an instrument that you launch into space, like on the Curiosity rover or the Perseverance rover, for example. These are wonderful instruments because they're so small. They're tiny, they use very low power, very low data rates, but once you design them, you have to freeze the design a couple of years before you actually build the instrument and put it on a spacecraft, and then it can't change. You can't update it. You can't adjust it for new opportunities and new discoveries. When you bring the sample back to Earth, you can look at new things you hadn't thought of. So when my laboratory analyzed material from the Stardust mission that brought back dust from Comet Wild-2, we were looking for amino acids, which was not part of the initial mission goals, because technology had advanced so that we could do that. And that's one of the gifts that keeps on giving from the sample return. One of the great things that NASA does, and Osiris-REx is also doing this, is 75% of the sample we return is archived. So the science team will use a quarter of the material to answer its 50-some hypotheses they'll be testing. But 75% will go for scientists around the world, and in fact, future generations of scientists. Maybe your listeners or the children of your listeners, scientists not yet born, using techniques not yet invented to answer questions not yet asked.
That's incredible. Well, Osiris-REx successfully tagged Asteroid Bennu, and I believe that you've watched a little bit of our coverage of that, and there's a correction that you need to help me make.
So the touching of the asteroid surface was an end member in our testing. It was the best possible contact with the most compliant surface that we'd ever modeled, that we'd ever tested. So it was within the range of our testing, way better than we had ever imagined would actually be on Bennu, because the surface of Bennu is so friable, so soft, so fluffy and loose. Which also suggests that any meteorites coming from Bennu wouldn't actually survive to the surface of the Earth, making this an even more valuable sample. We touched the surface. The sample head on the bottom of the spacecraft, about 3 meters below the science deck, penetrated perhaps half a meter into the surface of the asteroid. Collecting material, we backed away. And the sample container was, it's like an old car air filter looking device, so like a cylinder that has a plastic mylar check valve to hold material in. And that little check valve was bursting at the seams almost with material. It was just packed full. So we had planned to do a spin maneuver to see how much sample we had to measure it by measuring the change in moment of inertia of the spacecraft. Like, the story of the figure skater with arms in versus arms out, they change their speed. The same trick of physics we'd be using as a way to weigh the sample. Well, doing that would throw sample out, and every precious particle is someone's PhD dissertation. And so we estimate that we perhaps lost 10 grams while taking images. And so for perspective, that is more sample than every non-lunar sample return mission to date combined was lost. So we wanted to make sure that we could store that sample in the sample return canister before losing more. We were quite confident that we had at least 60 grams, which is our requirement. Probably hundreds, if not thousands of grams. So that's all secured in the sample return canister and safe. And there was no issues locking it up. It was just a very slow process because unlike the sampling, that's all autonomous. This was ground in the loop. So there's an 18.5-minute one-way light time So you do a command, you move the sample head, make sure it's in the right spot. You send the transmission back and forth, then you move it again, back and forth, and move it again. So it was an agonizing couple of days.
But as you were telling me off air, there was no risk of losing everything, as some media and possibly even us as well were sort of hyperbole with what was happening. But there was no risk of losing absolutely everything and having a mission failure, as it were.
Certainly not. No, certainly not a mission failure. Mission success was touching the surface. We'd achieved that. We just wanted to maximize the amount of sample, maximize the science. And so that's why we decided it was better to still the sample without measuring the mass, which would lose material. We did careful measurements to make sure that the sample return canister could close and that the sample head could dock. We had procedures if that wasn't the case. There's something called a boot scraper maneuver where we could scrape off material that was on the outside that wouldn't fit. None of that was necessary.
Well, that's fantastic. And now the next critical phase of the mission begins very, very soon in the next couple of months. The return journey to Earth with that precious cargo on board. And Hayabusa-2 is the Japanese mission that is just a few days away now from coming back to Earth here in Australia at the Woomera testing range. So I guess you guys on Osiris-REx will be looking really closely at how that goes and getting some pointers for Osiris-REx landing in Utah, I believe it is, in a couple of years. Correct.
So the Hayabusa-2 team and the Osiris-REx team are in collaboration. We've exchanged team members, exchanged information. We will be exchanging sample. So NASA will be giving 0.5% of the Osiris-REx sample, however many grams that is, to JAXA in exchange for a percentage of their material. But we've also just exchanged knowledge. It's a very friendly, open team because science sees no borders. I'm on the soluble organics team for Hayabusa-2 under Professor Hiroshi Naruka of Kyushu University in Fukuoka. And so I'll be helping him to analyze the samples from Hayabusa-2. So that's very exciting. And what's more, we can compare the superficially similar shaped asteroids on the ground. We will look at the samples in the same methods and just compare apples to apples to see how Ryugu material compares with Bennu material. Because though the asteroids are similar shaped, the spectra are quite different. And so they come maybe from different sources. We'll find out.
Well, it's certainly going to be a watch this space kind of excitement, really, as these samples come back and we can start analysing it. I think it's really fascinating that 75% of Bennu is going to be archived. For me, as an outsider, it doesn't sound like a lot is going to be used in the current studying, but certainly plenty of material to work with.
The mission plan from way back in 2010 was designed based on instrumentation at that time to do a grassroots work your way up estimate of how much sample we need. That's why we just figured out we need 60 grams to be able to get 15 grams to analyze and archive the rest. Wow. Having more material means we can do analyses that we call overguides, analyses that require more sample or look for more subtle materials, or since we see different distinct lithologies on Bennu, different types of rocks based on the spectra, we can do the same measurements on different pieces as we see them.
Well, that is very cool. And 2020 has... we're talking about Osiris-REx, the mission, parameters set in 2010. Fast forward 10 years' time, no one could have predicted what 2020 would bring. How has COVID-19 and the coronavirus affected the team in the way that operations were achieved, tagging the asteroid just a couple of months ago in the height of all of this?
It was very difficult. So we had to postpone some of our operations. We relied on, for example, the DSN telescope in Spain as they were having a peak corona problem, and so we had to make sure that we weren't stressing out that skeleton crew operating the telescope, operating the antenna. We all had to work distance. So I normally would have gone to Colorado to cheer on the spacecraft sampling and enjoy the party, and then spend the next few weeks analyzing the data to decide if we had enough material and be ready to stow. Well, it wasn't safe, so I didn't travel. I stayed in my dining room where I am right now, at the same computer, and for the analysis and a few very small things. So that's a little bit sad, but this is not the first unexpected thing that's happened. Our initial principal investigator passed away shortly after being selected. Oh. So we lost our leader soon after. Now, Dante Loretta has risen to the challenge very well, but that was unexpected. There were blizzards, a fire, an internet outage that also crippled one of the DSN communications until a last-minute intervention. The asteroid was a surprise. We had predicted accurately based on ground-based and space-based observations from Hubble and other telescopes that the asteroid was the shape it is and had the rotation it is, and we measured the thermal inertia, that is how quickly and slowly the temperature of the surface heats up and cools down in the day-night cycle. You can use that to figure out the grain size of the surface, and we figured out, this very smooth object with centimeter-sized pebbles, so this would be very easy to get a sample from. Well, it turns out that a thermal inertia measurement was correct, but our interpretation was totally wrong. Bennu is the shape we had predicted, but it's covered in these massive boulders, nowhere near what we thought. And so it turns out that these boulders are just not very well held together. So it thermally behaves as a pile of pebbles, but it's a mountain. And so we were able to prove that when we sampled by digging into the surface, as well as observations in orbit. So that was a surprise. Also, we discovered that Bennu was ejecting rocks. 5-10 centimeter rocks were being ejected while we were at Bennu, and so it's an active asteroid. Perhaps creating a Bennu asteroid shower in the southern hemisphere every September. It'd be a very small shower, but people are looking for it. So that's exciting. But it was frightening before we realized that these objects were too small to pose a risk to the spacecraft. Lots of challenges.
Yeah, well, lots of challenges. Hopefully from this point on, Jason, it's smooth sailing back to Earth. I'm going to let you get back to work because there is so much still to do with Osiris-REx. And as we said, Hayabusa-2 just a few days away now from the sample returning to Earth, hopefully. And there's plenty of analysis to be studied there as well. So thanks so much for your time today, Jason. I really appreciate diving into Osiris-REx, and fingers crossed we can have a chat again as it nears Utah in the years to come.
Thank you. Live long and prosper.
Well, Hayabusa-2 will bring back valuable samples of Ryugu for study, but what can we learn from them, and just how much of a sample is needed to make discoveries? As Jason was saying there, not a lot, but from a geological point of view, a geologist studying these samples, how much is required? Professor David Flannery beamed in for a chat earlier in the week. And Professor David Flannery is beaming in for a Trekzone conversation right now. David, thanks so much for your time this morning.
G'day. Thanks for having me.
Now, Hayabusa is coming, we're gearing up to this coverage on Sunday of the sample returning to Earth. It's going to be landing in Woomera. Osiris-REx is coming as well. That tagged asteroid Bennu a couple of months ago. And NASA has the Perseverance rover on the way to Mars for a sample return mission of its own. There's so many samples coming back to Earth from across the solar system. In your field of Earth sciences, what does that mean for you?
It's definitely a really exciting time to be alive. I guess it's worth remembering that we have had naturally occurring sample return missions from many of these bodies in the past, including the rocky planets of the inner solar system and asteroids, come to us in the form of meteorites. We're fairly sure we know where they're coming from, But to be able to go and get pristine samples ourselves really helps us peg our observations and test the hypotheses we've had for decades.
It really makes all the difference, doesn't it? Being able to go from theorizing about how stuff happens and how stuff works to actually being able to put the rocks under a microscope and definitively have answers to some of the questions, and also probably create some more questions as well.
That's right. I mean, a lot of the meteorites that we have are altered on their way through our atmosphere and on the surface of our planet. And so when it comes to getting pristine samples of asteroids, for example, we can learn about the building blocks of the world that we know, life as we know it, organic molecules that were present before life evolved on Earth, also where Earth's water came from. And when it comes to Mars is a bit of a special case because we're able to test a lot of these ideas we have about the possibility that life evolved on Mars as well as Earth. We'll be studying these samples, I think, for decades, just as with the Apollo missions. Anything that comes back from Mars in particular will be studied for a very long time.
Now, you're born and raised in Australia, but you are working with NASA on the Perseverance rover as it heads off to the Red Planet. It's on its way, and it's going to be the first sample return mission to the Red Planet. How is that? What's that experience like to be able to know that you're part of a team that are going to be getting samples from the Red Planet back for the first time?
I guess the novelty does wear off after a while. So these missions have a fairly long spin-up phase, about a decade. That's a short example with Perseverance. But you do have to pinch yourself every now and again and remind yourself that you are part of a much larger team that may look for or may even find evidence for a second genesis of life and hopefully get some of these samples back to Earth.
And I guess that's a little bit of a thing there as well with people in the public, and I've found this through the 8 years of podcasting that we're on the outside looking into these missions that are very exciting for us. There's so much new stuff happening, but as you say, there's such a build up to these missions that it just becomes another job really for you. Just we're off to Mars. We're going to get another sample, but I guess when it sort of comes back and it's in your hands, it makes it all worthwhile in the end.
I mean, these will be the first samples anyone's ever returned from Mars, so that'll be monumentous or monumental. But in terms of operating on Mars and sending hardware to Mars, after a couple of years of seeing objects the size of a grain of sand every day transmitted back from the Martian surface, it does wear off a little bit.
There still is that unknown of Mars, though, knowing exactly. I mean, I've just been working on my garden here in Brisbane for the better part of the weekend. It's full of clay, so very hard to dig into. We still don't we have an appreciation for what the soil is like on Mars, but there are still those unknowns, aren't there? Sticking a shovel, as it were, into the soil.
Yeah, there are lots of different reasons people want to get back different parts of Mars. The regolith is fairly well understood, and the dust that covers Mars has a global distribution and composition. But in the case of the Perseverance mission, we're going to investigate a package of really old rocks, really older than we've ever been able to investigate before. And that's significant because Mars in the past was very different to the way it is today. It seems to have been a lot more habitable, much warmer, a lot more water around, maybe a magnetic field to protect organisms from radiation. And so we'll be able to sample these rocks that represent this habitable time period, and we'll target those to return to Earth, looking for evidence of life. But there are many other reasons we'd love to get rocks back from Mars. For example, to date the surface. So we have relative age dates for the Martian surface based on the density of cratering. So the older a surface is, the more craters it should have. But we don't really have any dates to peg our relative dates to. So that's another reason we want to get material back. And there are many other people working on many other problems that each have their own samples they'd like to bring back.
And it's still only going to be a very small sample of Mars, isn't it? As we see here on Earth with different soil types around the planet, it's going to be the same thing on Mars. So this isn't the be-all and end-all mission, but it's certainly the start and a very exciting prospect to get those first looks at what Mars is like.
In some sense, that this is the most difficult part because we're trying to understand the context, the geological context. and take the best possible samples. And then to bring those back will be a technical challenge. But we want to make sure we've got the best possible samples first, and we really understand what we're bringing back. Each sample we'll cache is about the size of a pencil. So not very large, but a huge amount of material with modern analytical techniques. You could spend a lifetime studying just a tiny part of that. And you see that with sample return missions to smaller bodies in our solar system, maybe interstellar dust, for example. You only need a few tiny little particles that people can really learn a lot from.
You know, I was fascinated about that, talking with Jason Dworkin from NASA Goddard about Osiris-REx, that it's only a couple of 100 grams of material that they've picked up from Bennu. And as you say, we don't need a lot these days to really analyse the inner workings of this soil sample. And it really makes it, I guess, it still is a massive technical achievement to get it back, but a little bit simpler that it's not a couple of 100 kilos of rocks.
Yep. And I guess it depends on what you're looking at. A lot of bodies in the solar system are fairly homogeneous. The surface of the moon is fairly homogeneous in terms of its composition, but there are reasons we might want to visit other places. So we got a lot of material back with the Apollo missions and smaller amounts with the robotic sample return missions led by the Soviet Union. But it turns out most of those samples may have come from a single impact basin. And so all of the dates we have for the age of impacts on the moon, which inform our understanding of the entire inner solar system and how easy it might have been for life to originate on Earth, could all be affected by the fact we only went to one place. And so there are lots of reasons to make sure you get the best samples from the places you really need to go. And Mars is a very diverse place. It's not all made of lava like the moon. We have, like on Earth, a huge diversity of sedimentary rocks and different elements that we'd like to bring back.
And can the samples returned give an indication of the best place to put a colony on Mars? Could it sort of work in that way, as well as looking at the history, looking to the future of the planet?
Perhaps. I guess the more we learn about the surface, the more we know about what it would be like to live on Mars. I'm a bit of a skeptic when it comes to the concept of humans living on Mars in a colony. I don't see any economic or political or religious reasons to do it. It'd be a very challenging thing to do. We will know more about those challenges as we better understand the surface.
Sometimes it comes down to a little bit of doing it because we can, which maybe isn't the best reason to do something.
Maybe not the best reason if it's costing hundreds of billions of dollars to get the first humans there and much more to keep them alive in probably a fairly miserable environment, as far as I can tell.
Thinking about that, though, we would be able to get very specific rock samples and be able to shoot them back to Earth. So maybe there is something there. But
yeah, I mean, there's an argument to have humans on the surface because humans can get a lot more done than a lot of robots. But there is also the need to trade off the cost of a single human mission might cost probably well over $100 billion, whereas the Perseverance rover is a flagship NASA robotic mission with a price tag of about $2 billion. And so you could send 50 of those for the price of one human mission. If you think about how robotic technology is getting a lot better, autonomous systems are getting a lot more capable, by the time we have humans on the surface, we probably have some really capable robots that can do the job more efficiently.
Well, I know Mars is your bread and butter, David, but is there something exciting about Hayabusa returning in the next week, Osiris-REx in the next couple of years? China's also sending a sample return to the moon as well. Chang'e 5's on the way. We're getting all these samples back. Is there something exciting from not just Mars, but looking at these other missions as well to be able to study and analyse these rocks floating around the solar system?
Absolutely. I mean, in regards to the moon, people have been thinking about this problem that I just mentioned of how old is that really significant episode of cratering impacts on the moon and also therefore on Earth. When did that actually happen? We haven't known the answer to that question for decades. We've been poring over the Apollo samples, but they're really only from one area on the moon. And so the opportunity to get more samples back is huge for that community. They can test all of these ideas they've had moving around in the community for decades. And the same can be said for these robotic sample return missions to asteroids. We're learning all about what the solar system was like in its very early days. I mean, what was the Earth like before the age of the oldest sedimentary rocks? So on Earth, we can peer back in time with the geological record, we really stopped in our tracks at about 3.5 to 4 billion years ago, because that's the age of the oldest sedimentary rocks that we have on our planet. Our rocks get recycled because our planet's alive. This process of plate tectonics and weathering destroys them. And so we really don't know anything about what the Earth was like in the first 500 million years of its evolution, but that is preserved elsewhere in the solar system. These asteroids are 4.5 billion years old, and they contain the building blocks of the early Earth. And so it's an opportunity to learn about the early history of our own planet.
Fantastic, David. Well, looking forward to Hayabusa's return in the wee hours of Sunday morning. Looking forward to all these other missions that are happening over the next decade. Learning more about the solar system. Learning about where the Earth has come from, where we're headed. Even it's going to be a fascinating time ahead for geologists, astrogeologists, and everyone in between.
I agree. It's an exciting time to be alive.
Is known to man, a dimension as vast as space and timeless as infinity. It's the middle ground between shadow and truth, between science and ingenuity, and it lies somewhere out there. Beyond strange new worlds and the spirit that defines humanity. It's a dimension of imagination where the adventure never ends and the Trekzone begins.
David Nagle himself, Richard Dean Anderson, thanks so much for your time. Australia's only astronaut, Dr. Andy Thomas.
When you make a film, you don't know which ones are going to be classics and which aren't.
Tim Russ, Connor Trenier, Grant Imahara, Larry Nemenchek.
It's an absolute pleasure to be here.
Welcome back to the Trekzone live stream. We are just moments away from that re-entry interface. This is our exclusive camera looking northwest where the spacecraft is coming from in Coober Pedy. A huge thanks to the Umoona Opal Mine and Museum for access to this camera. While we wait, let's keep waiting. Brad, incredible pictures from over Coober Pedy, Hayabusa-2 on its way now to landing in Woomera. The project retrieval team are standing by to retrieve that very precious cargo.
Here's kind of where, the hard yards, so to speak, start, that they'll have to get into the retrieval, find it, start the quarantine and sterilization process, validate kind of the content, so to speak, and then prepare it in the eventuality to get to the labs back in Japan at JAXA, which then it will be, that's when the science starts to happen, where it starts to be divvied up and split, including samples that will find their way back here in Canberra with my colleague Trevor Ireland at Earth Sciences to be studied. And so that's when, that's when the exciting things happening, starting to get your hands dirty, so to speak, with asteroid rock.
Absolutely. And speaking with Jason Dworkin and also David Flannery from QUT, learning about these sample return missions. And as Professor Flannery said, it's a fantastic time to be alive for geologists, for earth science studies. With all these missions going out to the solar system, Hayabusa-2 now on its way back to Earth. We've got Osiris-REx orbiting asteroid Bennu. The Perseverance rover is on the way to Mars to collect some samples of the red planet. And of course, Chang'e 5 from China on the moon coming back before Christmas. There's so much stuff from the solar system coming back that we're going to learn so much. We're going to be able to put theories into practice over the next decade or so.
Yeah, and this is an important thing for a couple of reasons. The technology's allowed these things to happen. And, you get the benefit where by getting the samples back, you can compare it to your observations and measurements from afar. So that builds up the database of what we see, on the surface versus what's on the ground. And at the same time, by getting these rocks back, you could do a range of different experiments and ones that are just not practical to send to those places. There's only so many things you can miniaturize or fit on a spacecraft. And as new techniques, as new science, as new results pop up, you can retest the samples or test new parts of the sample and keep updating. And people do this for the moon all the time, and people do this for other things and for meteorites that land. So this is really where the exciting science starts to happen.
And another thing that I learned in chatting with all these great people this morning is that there doesn't need to be a lot of sample captured. We're talking a couple of 100 grams here, not even a kilo worth of sample that we've picked up. Professor Flannery talking about how we can just have some interstellar dust and still learn a great deal. The techniques these days of putting stuff under the microscope is just so efficient that we can really, Hayabusa can really share the love and show many people its secrets.
Yeah, I think people have this view that we just hunk a rock in and a laser shoots at it. But no, you really take very small, fine sample pieces. Because one of the issues is once you take it out of containment and you start testing it, you already contaminate it, you expose it to Earth. And so there is these issues and these time limits of how quickly you have to act in analyzing the sample before your potential increase of contamination and an earthbound component, so to speak, can get on it or affect your measurements. So you try and seal and try and save away as much as you possible. And there are still tons of moon rocks from the Apollo era that have never been out of containment because they're still trying to keep them preserved for those future experiments. And, this will be the same with Hayabusa-2 and Ryugu samples.
And Osiris-REx as well, Jason Dworkin telling us that the bulk of what they capture is going to be locked away for future generations. And we're going across the solar system and getting these many different samples so that we can really gain an understanding of what's out there in the solar system and not just focusing on one specific area.
Yeah, Ryugu and Bennu are different asteroids of different types. They'll tell us very different things about the solar system. And even if you just think about planets, you can't say, all right, well, we dug up Earth so we know what Mars is like. That's the same analogy here. They do have different evolution. They do have different origins. They do have different compositions. And it tells us a lot about the solar system as a whole, their individual objects, and lots of exciting things that, as you said, that we can keep doing more of as the ability in our technology increases to build these types of missions. And the cost comes down of doing them. And the ability comes up and more people doing it.
Well, we have confirmation from Mission Control in Tokyo that the parachute has deployed to slow the capsule for its landing in the Woomera protected zone in South Australia. We're staying with you right through until landing, and we will have the JAXA live stream momentarily. But that fireball, it was a little bit abbreviated, not as bright as they were hoping. The mission briefing for press earlier in the week said that they were hoping it to be about half the brightness of the current moon phase. But we saw it there. We definitely saw it there on the Umoona Opal mine camera. We will have that on replay very, very soon. But let's take you over to Tidbinbilla now. Glen Nagle talking about communicating with the spacecraft. Glen Nagle joins me now from the Tidbinbilla tracking station in Canberra, part of NASA's Deep Space Communication Network. Glen, thanks for a little bit of your time on this morning's live stream.
Yeah, hi Matt. Great to join you again.
Now, we've had you on the show in the past talking about spacecraft and keeping in touch with these spacecraft. I wanted to just touch on the differences between, say, a robot heading to Mars or the Moon, or an Apollo spacecraft heading to the Moon, and Hayabusa-2 heading to an asteroid. How exactly do you maintain a signal lock on that?
Well, actually, it's fairly similar to what you would do with any spacecraft, really. I suppose the major difference between, say, a mission like Hayabusa-2 and dealing with NASA missions is you're literally dealing with a different space agency. The terminology can be a little bit different, although certainly the Japanese, they're incredibly professional, and actually they're really a delight to work with because they have enormous enthusiasm for what they're doing, but they also are very, very precise in their communications. So if they need something special done with their spacecraft, then, it's very sort of matter of fact, straight to the point of what they want done. I'll give you kind of a good example. So back in 2019, when Hayabusa-2 was doing the their touchdown on asteroid Ryugu, it was we were watching their live coverage that they were streaming out on the internet, and at the same time we're communicating with them online through our system, through the Deep Space Network. And it was very interesting just to watch the interaction of the controller at the console, who was managing little changes that they were wanting to do with changing the bit rate, setting up certain commands at particular times. So that very much live aspect of something happening live, in the sense of you've got to deal with round trip light time, of course, for the communications, but dealing with that one-on-one aspect with the people at the Japanese Mission Control Center, and just kind of also just the fun of watching them through their live web feed and seeing their reactions as we were doing things and going, hey, there's the person we're talking to. So it was really interesting to do. So it was a little bit different from that point of view. Yeah, it was a little bit different from that point of view. It was much more, when you're doing events like that, it's much more live and straight at the moment. There are things to do moment by moment, whereas we get other big missions when you're going off to Mars, say, it's just, you're just cruising there and some things that are going to come up, to that day, tomorrow, the following week, it's very planned out, whereas this was very much a very live, as it happens event.
And one thing I've actually never asked you is how does the communication relay work in terms of are you given the commands to send to the spacecraft, or is Tidbinbilla and Goldstone and the other sites a relay station? So you're basically just connecting the call, as it were.
Yeah, I mean, I quite often describe us as being the post office for space. It was always going to the mission teams, the mission scientists, who determine what their spacecraft is going to do and what commands they will send out. So they'll be basically writing, a small program. They will then send that to us via the Jet Propulsion Labs, which is a sort of central hub for the three stations in the network: Canberra, Spain, and California, and then we relay that out at the appointed time. So what we get is what we call an SOE, a schedule of events. And within that, there are going to be key milestones, things that you need to be set up, prepared for. The operator has to ensure that that their frequency sets are right. Some spacecraft have have offset frequencies for transmission and for receiving, and there's also completely different frequencies. There's also certain bit rates that you will send the information at. So higher and lower bit rates, it all depends on the configuration of the spacecraft, where it is, what it's, how good its earth pointing is, and so forth. So there's a whole bunch of factors that go into it. But yeah, it's the transfer of the commands from the mission science team through us out to the spacecraft, but making sure all those are sent at the correct rates, correct frequencies, and everything else. When information is coming back, same sort of thing. We get the data back. We don't see what the data is. We just know what the data rate is. We can tell about the size of the file packet, as it were, how many bits there should be, and then relaying that back through after eliminating noise and so forth from the signal, going back to the mission science team again. One of the aspects we do though, which is doesn't require require initial involvement of the science team is if there's a problem. So if a spacecraft was, say, to go into safe mode, so we lose lock on the signal, then there are certain procedures which are in our manuals which the teams train for during, prior to a mission even going, and during the course of a mission, of various scenarios that we can do, things that we can enact to ensure that we can get back online with the spacecraft as soon as possible. So there are certain set uplink commands. We can say, okay, we broadcast at this high rate, this high this power to try to lock back in on the spacecraft and get the initial bit of information that the science team will need to then recover operations on the craft. Because while we're doing that, we're also waking up that science team and saying, your spacecraft is sick, so you need to wake everybody up and get things happening. It doesn't happen that often, but it does occur every now and again.
And the name Deep Space Communication Network sort of implies deep space. Where do you guys sort of pick up with the mission and start communicating once the mission's launched? And in the case of Hayabusa, coming back to Earth.
Yes, it's a good point. We talk about deep space being everything about 100,000 kilometers and beyond. So third of the way to the moon, and then the rest of the universe. That's our working area.
Just a small purview.
We have just a small bit. So, but important to point out is that closer than that, there were two other networks. So we know about the Deep Space Network, that's ours, but there's also the Near Earth Network and the Space Network. It all comes under the one umbrella of an organization within NASA called SCAN, the Space Communication and Navigation Division. And so the Near Earth Network handles everything that's near. So it's everything from, a couple of hundred kilometers above the Earth out to, say, about 1,000 kilometers. So that covers your small communication satellites, your CubeSats, and varying other spacecraft, space station, through the TDRS satellite network, the tracking and data relay satellite system. And then you've got the space network that sort of handles everything sort of 1,000 and further out, so getting out to geostationary spacecraft. So all those ones we use for weather and the big communication satellites and so forth. And then after that, because that's out to sort of maybe 40,000 kilometers. After that, there's sort of a blank space, and that's us onwards from there. Say for an example like Hayabusa-2, we will be supporting tracking them along with the JAXA's own system, their antennas at Yasuda, and tracking the spacecraft on its return. We'll track it pretty much all the way in. So the last contact for us will be probably about 3 hours before entry interface happens for the return capsule. And then it's basically some ground tracking over at Woomera that will sort of help them with that. There will be also a lot of visual tracking that will be going on for the re-entry capsule. Straight after, of course, there is a maneuver. After the Hayabusa drops off the capsule, then it does a divert maneuver. So it's not entering the Earth's atmosphere as Hayabusa-1 had to. It's actually going to sort of scoot past Earth and will head off on another mission to another object, which it won't get to for another 11 years. It's really a long-term mission, that one. And so we will be tracking Hayabusa-2 after it passes by and continues on out. So we've got a number of tracking opportunities in the days and weeks following that. So yeah, we're basically from the time it leaves to the time it gets home.
And basically, in terms of this mission, dropping off the sample capsule back to Earth, saying goodbye for a couple of hours and then saying hello again for another 11 years.
Yeah, so it's really great to see that they know that their spacecraft is in such good health that and will have the fuel reserves that'll be able to achieve that much longer term goal. You always like to recycle your spacecraft if possible. I mean, that wasn't possible with Hayabusa-1. It was, the spacecraft was really in a critical condition, so it came to a fiery end, quite a spectacular end. I know you're going to be sort of there right now, and you're broadcasting to your listeners as Hayabusa-2 returns, I remember, being there and actually being online and chatting with people as the first Hayabusa came in, and they were doing a live stream from, Western Australia, and images were coming through from the as an aircraft that was flying in the area, seeing if they could spot the entry capsule, and ended up with this really spectacular footage of the spacecraft coming in, and then this little tiny dot appearing underneath it, which is the return capsule, and as the mothercraft broke up and the capsule continuing on. So it was actually a really emotional moment. So I hope everybody watching this entry sort of has that same emotion, thinks back to Hayabusa-1 and what it was able to achieve.
Fantastic, Glenn. Well, appreciate a little bit of your insight here into Hayabusa-2, and also checking in with Spacecraft. And as more missions head out, I'm sure that we're going to be staying in touch and learning more about how all of this stuff works.
Yeah, there's lots more coming up. We've got a couple of missions arriving at Mars in early 2021. We've got our big dish coming back online with its work with Voyager 2 and other spacecraft. And it just continues to be really proud work that we do here on behalf of all these space agencies, with the CSIRO here, of course, running the station on NASA's behalf. So we look forward to bringing you much more excitement in the exploration of space.
Well, we are standing by to bring you live coverage from the Japanese Space Agency of Hayabusa's capsule landing in Woomera. But before we get there, I want to show you this. In case you missed it on the live stream, look to the top left of your screen and you will see that fireball coming in momentarily. There it is there. This is all thanks to the Umoona Opal Mine and Museum in Coober Pedy. The re-entry interface was a sight to behold, although it was a little bit less conspicuous, if you will, than what they had originally hoped. But hearing from Mission Control as well, there's a briefing going on at the moment on the JAXA live stream, which we are just about to take you to. They explaining that the beacon has been acquired and we are just about to enter into the very first or the start of the landing window. So the earliest opportunity for this craft to land, this capsule to land, is now. And I think that we will take you live now to the JAXA live stream as we await Hayabusa.
And the zoom up. Can you repeat or replace the movie of zoomed up fireball? Yes. Yes, replay. Yes, this is the direction of the great dog near Aldebaran. The first degree. This is the northwest, near the Nagle of the Orion. This and here, this is very high and near the zenith. And this is between two bright stars. This is the alpha and beta of the Centaurus. Both are the star of the first degree of magnitude. Taurus is actually the closest star to the solar system among the bright stars. I said it's close, but it takes 4.3 light year. Why you, Mr. Okawa, you know the constellation just from this image? Yeah, because this is my hobby to watch stars. Yeah, this is a control room at Sagamihara. So people are gathering around the product manager. They are watching, they are seeing Google Earth and discussing where the capsule would land. But beautiful movie. Can you show my PC? Yes, it's.
はい、ありがとうございました。
Thank you. Yeah, I can see it through my PC. Mr. Hosoda, can you hear me? Yes, this is Hosoda at the control room. So, yeah, they were watching Google Earth. Yeah, this is a map. So just by watching map, they can expect that they should be there. So everyone says different things. Yeah, very good atmosphere. They relaxed. And there is another image or movie. And this is from control room. There is a big news. From the international station, the station captured the Hayabusa-2. Can you show the movie? The ISS is where the Mr. Noguchi has gone and where he is staying. Wow, they made a trial. Oh, great. Can you switch to the slide?
It means that from ISS, the fireball could be seen. Okay, the replay, the image. This should be probably Hayabusa-2 itself. Therefore, from ISS, actually, it should be much higher than the ISS. So maybe ISS, took this image, the facings above. Yeah, therefore, there is a possibility that this could be the Hayabusa-2. Well, however, actually, I'm so happy because, from the ground and also from the space, the same Hayabusa-2 is being shooted. This is Hayabusa-2 or capsule. Sorry, I was too happy. Anyway, in the space, the Hayabusa-2 or capsule light is taken, right? That's right. Before this program started, actually, even when still, the Hayabusa-2 or capsule is receiving the sunshine, this images was taken, and at that time, probably the altitude of the Hayabusa-2 was much higher in altitude than ISS. And after that, it lost altitude and it fell down. It dropped much lower in altitude. Therefore, before this program started, this image was taken from ISS. In the support message, Hayabusa-2 is working so hard, but there is no more Hayabusa-2's photo, so it's kind of unfortunate. Therefore, Mr. Noguchi took it. Of course, we are not really sure if Mr. Noguchi took this one or not, but because other astronauts could have been taken it. However, anyway, according to the plan, already it's a time that the capsule should have landed. And if there is big news from the Australia, anytime we will let you know. And okay, here I'd like to introduce the preparation done by the capsule collection team. Okay, go back to the slide, and for instance, actually here we are looking for the capsule using beacon, and other than that, we have optical observation, and anyway, we are trying to use these kind of measures even for the fireball. And if there is no signal of a beacon, we have another one, the marine radar system. This kind of system was also equipped. And even if this doesn't work, we have a drone, and if we know that in the area of 100 and by 150 kilometers area, we will deploy drone to let them take a photo, and we will calculate by AI, and we will detect the location of the area that capsule landed. And after the capsule was found, and parachute must be detached so that it will not flown by the wind, and also there are lots of pyrotechnique. Therefore, anyway, it must be cut by the Nika, and also it must be packed and transported. And anyway, it has to go to the quick facility, and also that contains the gas inside of the capsule. And after that, it will be sent to Japan by airplane. And in Sagamihara, we'd like to start the initial analysis. That is a kind of procedures. And are there any movements in Australia? First, hello, this is Fujimoto in Australia. I'm Fujimoto of Umoona. The sound is not very clear, but still we can hear you. Please speak slowly. Actually, we traced the trajectory of the capsule by DFS, and now we will start the calculation of the landed place. Thank you very much. DSS is a detection finding system, and actually, this is the kind of a system using the beacon signal, and the signal was received. It means that probably the landed position will be calculated, and when the beacon signal was received, there are several lines, and the close point shows that instrumental module should be located there. Therefore, that's why they will go there. And actually, there is a kind of front heat seat and rear heat seat that is not emitting the beacon. Therefore, there is another way, not really depending on the beacon signal. But anyway, the instrument module has the Ryugu's sample. Therefore, anyway, such kind of measures is necessary too.
So we have explained the correction activity at Umoona, and I heard there's movies showing the preparatory work at Umoona. I want to show you. And this is Mr. Okawa. I think you remember when you were there. Yes, I remember the desert. Also, this is the desert. We have some low trees and some grass, and it's sometimes rain and plants. And you can see the earth, and there are many animals, some animals. What? Sheep or something? This is DFS. And this is rotating. and so that it can identify the direction where they can receive the strongest signal. This is drone. Yeah, this is a backup just in case when DFS cannot identify it. And also this is used for searching for the front and back side heat shield. We call this drone, but this is different from the drone we are familiar with. This drone is like an airplane shape. And when we make programming, they can fly so that they can capture the images without any omission. They continue capturing from the sky, and the AI analyzes and try to extract the capsule location. Now we will move on to Mr. Hosoda. Mr. Hosoda, can you hear me? Yeah, to studio. Yeah, we have Mr. Tsuda with me. So I would like to make an interview to Mr. Tsuda. Mr. Tsuda, how do you feel? Yeah, I'm really pleased. At the control room, we do not receive any wave, so we are now relieved and just listening to the report. That means waves are caught, received. That means the capsule have already landed, and I hope the helicopter will fly soon. Yeah, this is a beautiful story. We are also moved and inspired. So we continue working. The next one is Mr. Yoshihara, the capsule collection team. So Mr. Yoshihara, the capsule collection team. It's a perfect operation. Congratulations. So far. Thank you. The capsule is operation of the last day, so we have been looking forward to today. We are happy because every other member did a very good job, but we are under pressure because we also have to do that. But finally, capsule worked at the end. But still, we have not found sample yet, so we need to continue monitoring. Thank you. So we return the control to the studio again. Thank you. And now I would like to explain about the extended mission. Can you show us the slide about the extended missions? So we have completed the TCM-5. So that was we were successful in leaving the Earth sphere. So according to Mr. Hosoda, it's like the kid of elementary school, just go home, just throwing away the land back and going for another asteroid. So what asteroid is it going to? The next destination is 1998 KY26. It was not named yet, and it will arrive 11 years later. The size is very small, 30 meters. And it's spinning. It takes only 10 minutes for one rotation. and radius 1.23, and the orbit period 1.37 years. And we have started the extended mission, and we will experience swing by and fly by from another asteroid. And the rendezvous of the target is 2031, so 11 years later from now. So I said this is small. So LUGO is big as this, 900 meters compared to this. This is only 30 meters, like this. So when we compare it with Hayabusa-2, it's like 6 meters, so compared to 30 meters. So this is a comparison with Hayabusa-2. You can see this is very compact and it's spinning at a very high speed. And this is a relation between the diameter and the spinning period. The smaller the diameter is, the spinning period is also small, and this is a long scale. And the diameter is less than 200. And the rotation period is 2 hours in this area. Actually, we have not explored. Then this is one of the unexplored asteroids.
And as for the significance of the extension mission, actually, we have to increase, or you have to make the progress of the the long voyage technology, and also this is very high speed spinning asteroid, small asteroid. It means that the centrifugal power or force is very strong, and actually target marker can't stay on the surface of such kind of asteroid. And for instance, this is aggravated or just, the one rock, we are not really sure, and how to handle this kind of small asteroid. And also, it has to be a great contribution for the planetary defense. This is, the significance of the extended mission. Planetary defense, actually, this means that if this kind of asteroid or meteorite crash to the Earth, it's quite dangerous. That's why we have to prepare for that. Yes, that's right. Same as Ryugu and this one, KY-26, it is moving very close to the Earth, and if the timing is unfortunate, it may crash to the Earth. And actually, as for the smaller asteroids, there are so many celestial bodies in large numbers. Therefore, we have to know very well that is a great contribution for the planetary defense. And if we name this asteroid, maybe the person who found this asteroid has a right to name it. And actually, there is a kind of a group who like to find the stars, and maybe it was found in 1998, and therefore, as for the name, maybe we should discuss with that space watch who found this star. Well, actually, there are some reasons. That's why we cannot name it. So maybe some years later, maybe we can know. It seems if there is some more time, I'd like to talk about our campaign. Please go back to the slide. Don't you remember that you wrote your name? Actually, here is a kind of mirroring campaign too. Why don't we see the little prince of the star? Actually, I was forgetting to write my name, but probably the people who took part in this campaign should remember your name. Your name and the message were actually written on the memory of the target marker 7. And if you go to this page and if you enter your name, and you can know that your name is written here. And what is this shape then? Actually, this is the shape of the target marker. If two ones are kind of overlapped, actually this kind of outer seat, your names are written, and also capsule is equipped with memory, and in that memory, it has the same names, and that memory has come back to the Earth. And if you remember that you applied for it, please access to this site. Amongst the support message, actually some message said that it really has come back. There are so many such kind of messages. Yeah, it has really come back. Regarding the target marker, absolutely, the target marker landed on Ryugu, and some of them are staying on Ryugu, but the messages are in the capsule, and that came back with the capsule and came back to the Earth. That's right? Yes, that's right. It has come back. But however, there is one remaining, as you say. Yes, that's right. That's for the target marker. Two were left on the surface of the Ryugu, and two are, on the orbit of, the rotating around the Ryugu, and another one is still attached on the Hayabusa. Therefore, anyway, the remaining one will travel with Hayabusa-2 for 11 years, and it will go to the KY-26. Anyway, what to do is, the later I would like to discuss. Anyway, with curving our name one by one, the people who enter this project should be kind of feeling one of the family members of Hayabusa. And also, there are so many support messages that, the Hayabusa is something like, the family member of those peoples. Maybe we started this campaign about 6 or 7 years before, and in those I remember how I was feeling in those days. Regarding this kind of campaign, do you do this campaign? Yeah, not that just, but actually even at NASA, we do this kind of campaign. Therefore, anyway, wherever we go in the solar system, actually we should do it. And actually, this is not just somebody else's issue, but it's my own issues,
And this is from the control room. The Explorer will soon be ready for the next operation. That means it will go through the shade, and they will go back to the normal operation. So after the launch, 1 year after the launch, the Explorer did the swing by of the Earth, and while it is during the cruise, and as a period, basically using the solar battery. And even during the evacuation at the impact, it's hidden the UV, but it was in the area that can receive the solar rays. But after 4 years, the Explorer was in the shade.
All right, we're just going to break into that. Obviously, some delays in getting to the capsule. So at this stage, we are probably going to take a break and see how we go. We're fast approaching the end of when JAXA said they'd be live streaming as well, so we might be fresh out of luck in seeing the capsule land. But let's take a quick break and see what happens on the other side.
There's a dimension beyond that which is known to man. A dimension as vast as space and timeless as infinity. It's the middle ground between shadow and truth, between science and ingenuity, and it lies somewhere out there. Beyond strange new worlds and the spirit that defines humanity. It's a dimension of imagination where the adventure never ends and the Trekzone begins.
David Nagle himself, Richard Dean Anderson, thanks so much for your time. Australia's only astronaut, Dr. Andy Thomas.
When you make a film, you don't know which ones are going to be classics and which aren't.
Tim Russ, Connor Trenier, Grant Imahara, Larry Nemenchek.
It's an absolute pleasure to be here.
And you are back with me live here on Trekzone. No, the Opal Mine webcam has gone. Please let it go. The software as we go live. Let's take you back to JAXA now. Looks like they've gone back to mission control.
Applauses they made at the control area only today. But I can see that they're really pleased. Yeah, they're smiling. And also their voice has a very high tense. And the last thing is we find the capsule and confirm the parachute worked. And if we can collect good sample, that's really perfect. Report from Australia. We are looking forward to report from Australia. So while we are waiting, I would like to show you the video of separation.
Hayabusa-2 は11年をかける新しい旅に出発します。
Hayabusa-2 will now go on to a new journey. The target is This is only 30 meters, and this is the first attempt in the world to rendezvous with such a small asteroid. So first, we will use an ion engine to accelerate and go around 6.5. And during this period, we will do a new operation status and new issues. And since this is a long period operation, I think we'll be able to establish the energy-saving operation method. And utilizing this cruise period, Hayabusa-2 will do a scientific observation. One of them is the observation while changing the distance of the zodiacal light, so we can identify the distribution of dust. And also we will observe the transit phenomena.
Well, let's just break into that again as well. Obviously, still waiting for confirmation from Woomera of the return of the Hayabusa-2's sample collection capsule. We had some incredible pictures that have come through now of the returning. Here we are from the Umoona. I keep wanting to say coal mine, but it's not. It is, of course, the Umoona Opal Mine and Museum. Top left of your screen here, it should be coming through, if I've got that right. And I haven't got that right, so if we take on to the next one. Here are the actual images coming through. This is absolutely incredible as the fireball blazes across the Coober Pedy sky as that sample container returns to Earth. As I understand it, it has landed. They need to track it down. Obviously, it is absolutely pitch black in the Australian outback right now. And the Woomera protected area is the size of the country of England, as I understand it, which is just absolutely incredible and mind-blowing when you think about it. So some comments coming through. Some comments coming through on Trekzone's social medias of what is happening. And as we sort all that out, we are getting some incredible pictures coming through of Hayabusa-2 returning to Earth after such a long mission to asteroid Ryugu. It has those samples on board, and JAXA is tweeting that the helicopter search now is underway, and very much looking forward to that. We can finally get our hands on that very exciting asteroid samples. Now, Hayabusa's mission has three objectives: to expand our scientific knowledge of the universe, for Japan to develop unique technology for outer space exploration, and to venture to new frontiers. It's carrying the first ever subsurface asteroid sample and one of only a few extraterrestrial samples to have ever been brought back to Earth. Of course, we're talking the Apollo moon rocks, the Russian or the Soviet Union moon rocks, and now asteroid Ryugu as well. It's a significant milestone for the Australian Space Agency, who weren't in existence in 2010 when the first Hayabusa mission returned to Woomera back in 2010, as I said. So having the ability, and Professor Fujimoto told Trekzone in a news conference a couple of days ago that it's fantastic to have the agency now. So instead of the Japanese Space Agency having to reach out to all the different departments in Australia, they can just go to the Australian Space Agency and everything happens for them. A lot more streamlined, a lot more efficient in the operation. And that's the whole purpose for the Australian Space Agency, as Dr. Brad Tucker and I have spoken about on Talking Science in the past. So looking forward to so much more. Gilmore Space creating rockets, Southern Launch Australia launching them into orbit. We have that access to a fantastic part of the globe. We also have the returning capabilities as well. As I said, the Woomera protected area, the size of England, which just allows for so little risk, if you will, of human collision if you will. Obviously, we don't want that to happen. We don't want people's houses to be dropped on by any returning spacecraft or very important samples from the solar system. It's been fun, this live stream. Jason Dworkin from NASA's Osiris-REx joined me to talk about their asteroid sample mission. They tagged asteroid Bennu a couple of months ago. The spacecraft is in orbit of that asteroid and will be heading back to Earth for a landing in the Utah desert in 2023. The commands for that should be sent out in the new year. Glen Nagle from the Tidbinbilla tracking station. I always love having a chat with him because he's so passionate about what they do out there, and they've been doing it for so long as part of NASA's Deep Space Communication Network. They're the critical link, along with Goldstone and Madrid, to stay in touch with anything out there in the solar system. Future missions, Artemis to the Moon, Artemis to Mars, Osiris-REx, Hayabusa-2 on its extended mission, and of course the Perseverance rover. And Professor David Flannery from the Queensland University of Technology joined me to chat about what, from a geological perspective, what these missions can provide for geologists and in their studies of the early solar system. But beyond that as well, he is working with the Perseverance team for the sample return, or the sample collection and return part of Perseverance's mission. So for the first time, we'll be seeing Mars rocks on planet Earth, which I think is something absolutely fantastic and something certainly worthwhile waiting for. Hopefully it'll happen sometime this decade, but we will just have to wait and see. Let's take you back to the JAXA live stream. Let's see if anything else is happening right now.
Much for everything. And Mr. Hosoda in the control room, can you hear me? Yes, I'm Hosoda. Could you say the last word? Okay, thank you very much. Until the late. And actually, watching this explorer, all of us, is a fantastic moment and so happy work. And the director, Mr. Inat, says that. Actually, he showed a great smile, and because he had various hardships in the case of the first generation Hayabusa, and of course not just Hayabusa-2, but the JAXA will continue to have lots of projects. Therefore, anyway, based on this success, anyway, would you like to evolve ourselves? Thank you very much. And actually, Mr. Hosoda, I'd like to introduce you, the comment anywhere, and somebody, somebody would say that I was influenced by that we saw that time, that one I saw. That is the word of Mr. Hosoda. Actually, among the support messages, thanks to this project, some young people entered, the aerospace department in the university. Therefore, all the people who were involved in this project or have studied the project, everybody were so much impressed, and also all the people, in Japan and in the world, thank you very much for that, especially in Japan and in Australia. Actually, this is in the middle of the night or even, early morning, and this time, to be wake up, it's quite severe. However, anyway, we'd like to announce the end of today's, the distribution. Thank you very much for everybody. Good night.
All right, well, obviously, JAXA have wrapped it up. The recovery missions, or the recovery people, are out there now, searching by helicopter. The beacon is active, and so they have a location. They just obviously need to triangulate it and sort everything out. But we've lost our live feed, so let's go to a break and wrap this whole thing up.
There's a dimension beyond that which is known to man. A dimension as vast as space and timeless as infinity. It's the middle ground between shadow and truth, between science and ingenuity, and it lies somewhere out there. Beyond strange new worlds and the spirit that defines humanity. It's a dimension of imagination where the adventure never ends and the Trekzone begins.
David Nagle himself, Richard Dean Anderson, thanks so much for your time. Australia's only astronaut, Dr. Andy Thomas.
When you make a film, you don't know which ones are going to be classics and which aren't.
Tim Russ, Connor Trenier, Grant Imahara, Larry Nemechek.
It's an absolute pleasure to be here.
Well, welcome back to the Trekzone live stream. Matt Miller with you at Trekzone HQ. It's now just, well, I had the script as just after 4 in the very early AM, but it has just gone 4:30. And as you can see, if I turn that off, we don't want to see that. Live stream happening, throwing everything out the window. Look, we have had a very successful morning, at least in regards to seeing the... And once again, that has not loaded up for me. Well, that is live television. There we go. Let's have a look at that as the sample capsule has returned through the atmosphere. That beautiful fireball. It's a big thanks to the Umoona Opal mine as well for allowing me access to their webcam. The Project Retrieval team, as I said, are on the way. They've got the telemetry. They've got the beacon. They're doing the best they can. We will, of course, have a full wrap-up of this milestone for the Japanese space program on Talkin' Science on Tuesday, so be on the lookout for that one. It'll be episode 510. And just before we go, I want to remind you of what's to come from Australia's unofficial home of Star Trek in 2021. Well, we're definitely more than Trek now. With our huge change, and I'll read the script if you'll excuse me. We're going 7 days a week with 5 shows from January 1. That time when on Sundays and Saturdays we'll take you back to the podcasts gone by, reminding you in a bite-sized podcast of what we've done and giving you the links to catch the shows in full. We have such a huge back catalogue of shows that the best thing that I can do for new people finding us is to show you what we've done and hopefully encourage you to go and watch them in full. Trekzone Plays moves to Mondays and Thursdays, continuing to bring you 100% retro gameplay with no commentary. I've now completed Star Trek Away Team and Star Trek The Next Generation of Final Unity. Star Wars Dark Forces is coming up, but the first game of the new year will be the 25th anniversary Star Trek The Original Series game. Talkin' Science returns on Tuesday, January 5, with Dr. Brad Tucker and I discussing the latest science and space news headlines in a light and fun 30-minute podcast. I've really appreciated Dr. Brad's time this year. This live stream here is episode number 104 of Talkin' Science. So that'll be back bigger and better than ever before in the new year. A Trekzone Conversation moves to Wednesdays, and we'll continue to bring you the long-form interviews and detailed analysis of our favourite franchises. It's what we've been doing every Monday this year, and I've been so appreciative to all the guests that have stopped by to spend a little bit of time with me talking about what they love. Lee Sargent, my Talking Trek co-host, Dr. Trek himself, Larry Nemechek, Doug Drexler's been on the show, Tom Costantino, he's coming up in a couple of weeks to talk about the Orville resuming production on season 3, which is absolutely fantastic for them as COVID just runs rampant through the US once again. So be on the lookout for that. A Trekzone Conversation moves to Wednesdays in 2021. And lastly, Trekzone's The News is back on Fridays, keeping you in the loop with all the latest production news. It's the bite-sized podcast where we bring you all the stuff that's happening in our franchises that we love, covering off Discovery, Picard, Star Trek, Star Wars, anything else that's happening as well, and of course the Orville. So don't miss a moment, subscribe and ring the bell to get notifications. Never going to spam you, just going to pop into your inbox with the latest episode of Trekzone. Well, that's how we're going to be doing future mission coverage, a unique take on these fantastic missions. Thanks so much for your company, both live and on replay. I've had a couple of hiccups, but for a first major live stream, it went really well. Really appreciate those joining me live, the handful that we've had, which has been fantastic. As I said, we're going to have that full wrap-up in Talkin' Science on Tuesday, so be on the lookout for that. That's episode 510. And the interviews that I had today, they're going to be replayed on tomorrow's Trekzone conversation. For now, I'm Matt Miller at Trekzone HQ. Thanks so much for your company, both live on replay and, as I said, it's been amazing to capture this moment in history, the beginning of a slew of sample return missions coming home to further our understanding of the universe in this decade.